Welcome back. So we gained some familiarity with SGD, and today we're going to talk about high confidence guarantees. Recall we showed for SGD that basically the expected error is bounded by a bound that depends on some parameters, notably the number of iterations. For instance, we saw for convex and G-Lipschitz functions that the expected suboptimality gap, right? So our error was basically the expected the suboptimality gap. So let's say f wt minus f star. So this was bounded by, let's say, 1 over the square root of t. And for general non-convex functions, and in the case where the function was L-smooth, we show that the expected gradient norm was bounded by, again, 1 over the square root of t. Okay? So abstractly then, what we showed was that the expected error was bounded. Okay? So let's see what this means. This means that our guarantee says if you run SGD many times, on average the performance is well. Okay, so I get a performance on the first run, another performance on the second run, and so on and so forth. I take the average of all of these, and that's a good performance, right? So I get a very low error. So obviously this is not satisfactory, right? Because we want a good performance after only one time training. So ideally, I just want to train my model only once, and I want the model to perform very good. Okay. So mathematically, we can express this desire as follows. So let's say that we have some confidence parameter, delta, and we want with probability exceeding 1 minus delta. So delta, you should think of it as a very small number, like 0.1 or 0.01 or something like that. So with high probability, I want the error to be bounded. Okay, so that means that every time I run SGD, with high probability, I expect a good performance. Okay. Equivalently, the probability that my performance is not good is bounded by some very small number, delta. Okay. Now, the big question here is, can SGD deliver such result or not? Okay, because our previous result was not of this nature. So we just proved that the expected performance is good. So this is what we want to talk about today. Okay, so our first approach to answer this question is that let's see what happens when we impose stronger assumptions. Okay, so what was our main assumption last time? So we assumed that we have access to a stochastic Fessor oracle. Okay, so what that means is that my stochastic gradient is basically a noisy version of the true gradient, such that conditioned on how I have done so far, the noise is, the mean of the noise is 0, and also the noise has a bounded variance. Okay, so we just assume zero mean noise, conditionally zero mean noise, and bounded variance noise assumption. Okay. Now, if we make this assumption a little bit more stronger, it turns out that we can show SGD performs well with high probability. Okay. One way to do so is to assume that the noise is light-tailed or sub-Gaussian. Okay, so this is the condition of a sub-Gaussian noise. Essentially, what that means is if you consider the PDF of a Gaussian random variable, the tail of the noise is sort of bounded. So this is the tail of the noise distribution. So the tail of the noise distribution is sort of upper bounded by the tail of a Gaussian random variable. Okay. So examples of these are obviously the case where the noise is Gaussian, okay, or the case where the noise is uniformly bounded. Right. So so basically the tail doesn't go to infinity. That's what I'm saying. Now, if we impose an assumption like this, it turns out that we can resort to concentration of measure inequalities, which basically aim to capture the deviation of a random variable or a sum of random variables from their mean. One notable example here is the Asimov-Hoffating inequality. So using these kind of results, we can indeed show that our previous bounds hold with high confidence. Basically, the error of SGD. So that means for convex function, we are talking about suboptimality gap. For general non-convex function, we are talking about the expected gradient norm, is bounded by something that depends on t. So this has this previous dependence. So for instance, 1 over the square root of t that we saw before. And also it depends on the log of 1 over delta. Okay? And this is very, very good, right? Because you can basically treat log as a constant. Okay? So for instance, if delta is let's say delta is 1 over e to the 10, e to the 2, which is roughly 1 over 10, let's say. The log of 1 over delta is nothing but 2. So it's just a constant. Okay, so we can basically ignore the dependence on our confidence parameter. So that means that we can essentially have the bounds we established before that hold on expectation with high probability without any noticeable dependence on our confidence parameter. Okay. Now, let me talk very briefly about the key idea to leverage these kind of assumptions and how we can integrate this idea with the theoretical tools we developed so far. And to do that, we sort of require a very useful concept that's called the Martingale difference sequence. Okay. So let's go over the definition, and then I'll try to connect it to something that you may have seen before. Okay. So a sequence of random variables is a Martingale difference sequence if conditioned on another sequence of random variable, the expected value is 0. Okay. So the intuition here is that you should think of these as a generalization of zero mean independent random variables. Indeed, if I have a sequence of zero mean independent random variables, they actually form a Martingale difference sequence. So why do we need this? So in our context, in deep learning optimization, the x, which form these Martingale difference sequence, are typically basically the difference of your stochastic gradient and the true gradient. Okay? And what I'm interested to see is if I average these xi's over time, whether that average grows gracefully with t or not. Okay? Now, the issue here is that x1, x2, x3, x4, etc. are not independent. Okay? Because as we can see here, they depend on the current parameter value, wt, and obviously wt depends on the previous instances that I've used, let's say in my SGD algorithm. Okay? But if I condition on the previous examples, the expected value of this difference is 0, meaning that condition in my noise is 0 mean. Okay? Now, this, in addition with, let's say, assuming bounded noise or lighted noise, helps us to basically leverage advanced concentration measuring inequalities, such as the Asimov-Hoffating inequality that I mentioned, to show that the growth of the noise terms, basically terms like this, that we actually studied when we analyze the performance of SGD, grow very gracefully with t. So essentially, using this Martingale difference sequence idea, and a stronger assumption, we still can hope to get the same good dependence on the number of iterations, and also a very good dependence on our confidence parameter, notably log of 1 over delta. So that's basically the main idea. So we can easily leverage this to the theoretical tools we talked about before. Okay, so, but the catch is the following, that this assumption could be violated in practice. Okay, so in practice, especially in the context of deep learning optimization, it has been observed that the noise is not long tail. Okay, so one remedy, which could be very intuitive, is that you perform clipping or normalization. So what does that mean? Let's say that, again, I have a stochastic gradient, which is a noisy version of the true gradient. Instead of using this directly in my SGD algorithm, I'm going to clip it. So basically, I'm going to ensure that the gradient coordinates are not larger than, let's say, some constant c, and are not smaller than some constant minus c. So this is called clipping, okay? And this operation is applied coordinate-wise. Alternatively, I may normalize the gradient. So both of these ensure that the update vector that I'm using is not too large, okay? Therefore, I should be able to control the noise of the updates, and using more advanced theoretical analysis, we can show that the resultant algorithms could deliver high confidence guarantees. So the main challenge in those theoretical analysis is to deal with the bias that you are introducing when you perform clipping or normalization, okay? Because if G is an unbiased estimator, the clipping of G or the normalization of G is not going to be an unbiased estimator of the true gradient anymore. And the impact of this bias needs to be studied very carefully when performing convergence analysis. What I want to mention beside this is the connection to advanced training methods. For instance, adaptive algorithms that we're going to talk about in this course, and also other contexts, such as making algorithms private. So the idea of clipping and normalization turns out to be useful in these two contexts as well. And this is something that we're going to talk a little bit about later on in the course. Another useful thing to know is that these ideas also appear in diverse learning settings. So one example is the celebrated PPO method that's used very frequently in reinforcement learning. There is also, you can observe the idea of clipping having an appearance. So, and it is, if our purpose is establishing high confidence guarantees, it is important to leverage sometimes these safeguarding mechanisms, because otherwise the growth of the accumulation of the noisy terms could be larger with respect to delta. So that means that we may not be able to get this very desirable dependence on the confidence parameter. So we may get something that is potentially significantly worse. Okay. So that's basically one answer to the question whether SGD can achieve high confidence guarantees, and the answer is under a stronger assumption, yes. If not, we may have to modify SGD in certain ways. One particular way is to clip the updates or normalize the updates. Another way is by way of boosting or ensemble of SGD that I'm going to talk about for the remainder of the video today. So the idea here is that given that we're not going to impose the bounded assumptions anymore, we cannot use those nice and advanced concentration measure inequalities. All we can use is the basic Markov inequality. Okay. So let's see what's Markov inequality and what's the implication of that for high confidence guarantees of SGD. So Markov inequality is very simple. It just says that for any positive random variable x and any positive constant lambda, you can basically bound the deviation probability of x. So the probability that x is larger than lambda is bounded by the expected value of x divided by lambda. So all we need is for the expectation to exist. So we don't need any assumption on the variance or higher moments. All right, so what's the implication for us? So let x to be the error. Again, the error is a random variable because it's the error of our randomized algorithm SGD. And let lambda to be the bond we get, let's say from one of our previous theorems, divided by delta, our confidence parameter. Then by Markov inequality, it's very easy to see that the probability that the error is larger than bond over delta is upper bounded by this expression. So I'm just plugging in what x and lambda are. And recall, we were able to show that the expected error was less than or equal to bond. So whatever this ratio is at most 1. So I can replace upper bounded by 1, and therefore the probability that the error is bounded by is exceeding bond divided by delta is at most delta. So equivalently, with high confidence, we can say that the error is bounded by the previous bond, let's say 1 over the square root of t, divided by delta. So with this very simple inequality, therefore, we can indeed establish a high confidence guarantee for SGD, but it is not a good guarantee because we now have a very terrible dependence on our confidence parameter. The dependence is now 1 over delta as opposed to log of 1 over delta. Okay? So if delta is small, I can treat log of 1 over delta as a constant, but surely I cannot treat 1 over delta as a constant. Okay? So we are looking for a way to sort of improve upon this result. And the idea is actually very simple. We just want to boost SGD, right? So essentially, you can think of SGD as a weak learner, and we want to boost SGD, meaning that we want to put together a bunch of these weak learners in a specific way, such that we get a strong learner out of it. Okay, and this is very similar to the idea of model assembling in machine learning. Okay, so let's see how do we approach boosting SGD. So the idea, as I mentioned, is very simple. We're going to run multiple SGDs in parallel and perform a simple post-optimization step. Okay, so therefore the algorithm is as follows. Let capital S denote the number of parallel runs, and let n be the number of data points that we're going to use in the post-optimization step. What we're going to do is that we're going to run S versions of SGD in parallel, and let's say store their outputs. And in the post-optimization step, we're going to select the best output. Okay. Now our selection requires us to have an estimation of the true gradient. That's why we use capital N number of data points in the post-optimization step. So we use these data points to approximate the true gradient, and then we're going to find the best output, the output that has the lowest gradient norm. Okay. And know that instead of the gradient norm, in practice, we may use the function values. So both of these are good ways of talking about which solution is better, right? Because when I'm minimizing a function without any constraint, both of these mean that I'm going to have a solution, have a good solution. Okay. Okay. So let's talk about the total complexity of this algorithm compared to a stochastic gradient descent. Okay, so in SGD, we said that the total complexity is B times T. And the reason is that our mini-batch size is B, and we run the algorithm for capital T number of iterations. Therefore, overall, we're going to perform B times T gradient computations. And if we treat B to be a constant, then the total computation is basically O of T. Okay. In this case, however, the SGD with post-optimization algorithm has a total complexity or oracle complexity, which is as follows. We have S versions of SGD. We are running them on parallel, and we run each one for T number of iterations. In the final step, the post-optimization step, we want to select one out of S solutions. Okay? And to do that, we perform N gradient computation per solution. Therefore, the total number of gradients that we calculate is N plus T times S. Okay. Now, what is desired is that this number is roughly the same as the complexity of SGD, while resulting in a high confidence guarantee. And what we can show is that indeed, we can set N, T, and S such that with minimal increase in the number of gradient computations, we can boost SGD and get high confidence guarantees. Okay. In particular, we have the following theorem that says that if the number of samples used in the post-optimization step is given by this expression, the total number of iterations for each of those parallel SGD runs is given by this expression. And this is exactly what we had before for SGD. And finally, if the number of SGD runs in parallel, S, is given by this expression, SGD with post-optimization can find a solution such that with high probability, the expected gradient norm is small. Okay? So we said that the total complexity is N plus T times S. So if we use these expressions given in the theorem statement, we can find that the total complexity in terms of the quantities of interest, notably our notion of performance epsilon and our confidence notion delta, is given by this expression. Okay? So there are two terms here. Okay? The first term, in terms of epsilon, is the higher order term. And the second term is the dominant term, okay? Because it has a worth dependent on epsilon. So let's compare the second term, which is the dominant term in the bond, in the total complexity bond, with what we got for SGD. So for SGD, we said in terms of the expected performance, so expected performance of SGD, the dominant term was 1 over epsilon square. And the simple result we got while leveraging the Markov inequality said that the high confidence performance of SGD we got 1 over epsilon square divided by delta. Okay, so therefore we can see that as a result of doing SGD with post-optimization, we can improve the dependence on the high confidence parameter quite drastically. So that dependence improves from 1 over delta to log of 1 over delta, which is very, very desirable. Okay. And essentially, the total complexity doesn't change much compared to just one single run of SGD. Okay, so compared to just one single run of SGD, we have to spend log of 1 over delta more computations. Again, this is like a constant. So what this means is that in practice, all you need to do is to get a higher confidence performance out of SGD is to run, let's say, 3-4 SGD methods in parallel and then perform this post-optimization. And the result tends to be better and have lower variance than just a single run of SGD. Okay. Now the proof is actually quite simple, and we can carry out with that using the tools we've developed in the course so far. The crucial point is that we need to show that by leveraging ensembling or post-optimization, we can actually, as I mentioned, boost the simple Markov inequality concentration result that we got, and therefore improve the dependence on delta. Okay, so therefore we in this lecture we talk about some ways to either show that the SGD method we talked about achieves high confidence guarantees, and that was basically imposing a stronger assumptions. We also talk about some ways to modify SGD such that it achieves a bond with high confidence. One approach was based on clipping or normalization to control the amount of noise in each update. Another one was this idea of boosting, where we would run multiple versions of SGD and then perform post-optimization. In the next lecture, we're going to talk about another way to strengthen the power of a stochastic gradient descent. I'll see you next time.